Welcome. Uh, my name is Dr S Sathish Kumar, Department of EEE, Kumarasamy College of Engineering, Karur. I am going to handle the course Digital Logic Circuits under the topic Sequential Logic Circuits. Okay. Synchronous sequential logic circuits. So while you're coming to this sequential logic circuits, there are two types there. Sequential logic circuits, there are two types. One is nothing but synchronous. Another one is nothing but asynchronous. Okay, another one is nothing but asynchronous. What is the basic difference between this synchronous as well as this asynchronous? Okay, synchronous as well as the asynchronous. Synchronous, the common clock pulse. Okay, common clock pulse. So while you're coming to the asynchronous, see only one clock pulse. Okay, only one clock pulse. So this is a basic difference. Okay, while you're coming to the sequential, there is a synchronous as well as asynchronous. Is the two types, and next one is nothing but the common clock pulse, and one is the one clock pulse for the asynchronous. Next, the output will be accessed in clock pulse for the second one. So this will be repeated accordingly. How many inputs we are going to use? Accordingly, the clock pulse will activate the outputs. Okay. Okay, we can see the sequential logic circuits. Okay, sequential logic circuits. So while you come into the sequential logic circuits, the main we are going to use, that is nothing but flip flop. Okay, main we are going to use flip flop. Okay, we are going to use flip flop. So the flip flop is nothing but it's a memory element. Okay, the flip flop is the memory element. Memory element. So while you're coming to the flip flops, there are four familiar types of flip flops are there. Four familiar types of flip flop. Okay, four familiar types of flip flop. Okay, first one is nothing but RS flip flop. Okay, first one is the RS flip flop. Second one, okay, RS flip flop. Second one, JK flip flop. Okay. Third one, D flip flop. Okay. Third one, D flip flop. And final one is nothing but T flip flop. Okay. Final one is the T flip flop. Okay, the first one is the RS flip flop. Second one is the JK flip flop. Third one is the D flip flop, and fourth one is the T flip flop. So while you're coming to the RS flip flop, R stands for an reset, that value is 0. S stands for an set, that value is 1. Similarly, J stands for an set, that value is 1. K stands for an reset, that value is 0. So here D stands for an data or delay flip flop. Okay, data or delay flip flop. Okay, data or delay flip flop. And finally T stands for an toggle flip flop. Toggle flip flop. So these are all the various types of flip flop. Four familiar types of flip flop. RS, R stands for reset, the value is 0. S stands for set, that value is 1. J stands for set, that value is 1. K stands for reset, the value is 0. And D is nothing but data or delay flip flop. And finally T is nothing but toggle flip flop. Okay, first we can see RS flip flop. Normally, all the flip-flops are designed by using 2 NOR gates or 2 NAND gates. Okay, 2 NOR gates or 2 NAND gates. First, we can see RS flip-flop. While coming to the RS flip-flop, we are going to draw its circuit diagram. Okay, circuit diagram. Circuit diagram. Normally the flip-flop consists of 2 outputs. One is normal output, another one is nothing but inverted output. Inverted output. And clock pulse. Clock pulse equal to 1. This is R and this one is yes. So inputs and this one is nothing but outputs. Okay. The first AND gate, second AND gate, first NOR gate, second NOR gate. So first we can write its truth table. Okay, truth table. So clock pulse, inputs R and S, next outputs, and finally something but state. So when the clock pulse is 0, there is no consideration of R and S. So Qn and Qn bar state. So no change. Okay, no change. So the state will be no change. The previous output will be there. Similarly, when the clock pulse is 1, when I am giving 0 0 as an input, we will get the output that is no change. Okay, no change. When the clock pulse is 1, when I am giving the 0 1, okay, I am giving high value to S. The S is nothing but set. The set value is 1. In Q1 we will get 1 and Q1 bar 0. So the condition is the state is set. So when the clock pulse is 1, I am giving 1 0. High value is given to the R is going to reset. The value will get 0 in the Q1 and Q1 bar it is 1. So the state is nothing but reset. When the clock pulse is 1, when we are giving the inputs, 2 inputs 1 1, we will get, that is nothing but indeterminate condition. We can't able to define that, undefined condition. Okay, undefined conditions. So when we are applying 0 0, so what is the output we will receive? We will get 0 0 here. So this 0 will access an input here. Similarly, this 0 will access an input here. So what is the truth table for NOR gate? 0 0 0 1 1 0 1 1. We will get, when both the inputs are 0, we will get 1 here. When one input is high value, we will get low value in the output. Okay, it does the reverse operation of OR gate. So 0 0, we can't able to predict what is the output here. So we are going to consider the previous output. I am concerned this is 0 and this is 1. This 0 will access an input here. This 1 will access input here. So what is the output? Here the 0, this is 1 here. So no change. We are assumed 0 here, we got the output 0. We assumed 1 here, we got 1 here. So no change condition is the output we will get when we are giving the input 0 0. And next 0 1 we are giving. So the output is 0 here. We will get 1 here. This 1 will access an input and this 0 will access an input. So when any one input is a high value, automatically the output is 0 here. So the 0 will access and feedback. So the output is 1. So we are giving the high value to yes, we got the output 1 here. Similarly, while you are giving the input 0 for yes and input 1 for R, what is the output here? The clock pulse is 1, so the output is 1, the output is 0 here. So 1, so the output will be 0, the 0 will access the feedback, the output is 1 here. So we are given the input high value to R is a reset value 0, we got 0 here. When 1 1 we are giving, the output is 1 1. So this 1 will act as input here, this 1 will act as input here. So 0 0. So in flip flop we have to get one normal output and inverted output. So we are getting both inverted output. So we can't able to define that as an undefined function here. So while we are giving input 0 0, we will get mode change. 0 1 we are giving to high value to yes, we will get set value. 1 0 we are giving high value to R, we will get reset. 1 1 we can't able to define that function here. So characteristics table for RS flip flop, characteristics table for RS flip flop. In characteristics table we are going to consider the present state, Qn, okay, inputs R is, the next output, that is nothing but next state Qn plus 1, okay, Qn plus 1. So 0, present state we can consider 0 and 1. So 0 0 here, 0 0 1 here, 0 1 0 here, 0 1 1 here, 1 0 0 here, 1 0 1, 1 1 0 here, and 1 1 1. So 0 0 no change. What is the present state? That will be appears on the next state. What is in the present state? 0, that will be appears on the next state. I am giving high value to yes, we will get 1 here. We are giving high value to R, we will get 0 here. 1 1, it will be indeterminate, we can't able to define the function. 0 0 no change, 1 0 indeterminate. It's a characteristics table for the SR flip flop. By using this we are going to derive the characteristics equation. So 3 variable K-map we are going to use here. So for Qn plus 1, Qn R is 0 0 0 1 1 1 1 0, 0 1 0 1 3 2 4 5 7 and 6. So 0 1 0 1 don't care 0, 1 1 don't care 0. Is it correct? Okay. So we can form quad here and we can form pair here. So Qn plus 1 equal to, what is the answer we will get? S plus Qn into R bar. Qn into R bar is the final answer for the Qn plus 1. S plus Qn into R bar. So next we are going to derive the excitation table. Okay, excitation table. So excitation table we are going to consider present state, okay, present state, next state, and flip flop inputs. Okay, flip flop inputs. Flip flop inputs is nothing but R and S. Qn plus 1 Qn 0 0 0 1 1 0 and 1 1. Okay, so we can write that characteristics table. By using that only we are going to derive the things. Okay. 0 0 0 0 1 1 1 1. So 0 0 0 1 1 0 1 1 0 0 0 1 1 0 1 1. So 0 no change, 1 0 don't care, 1 1 0 don't care. Okay, what are the things we are going to get? 0 0, present state 0, next state 0, present state 0, next state 0, present state 0, next state 0. Okay, present state 0, next state 0, present state 0, next state 0. Don't care 0. Okay, don't care 0. Similarly, present state 0, next state 1, present state 0 0 1. Next present state 1, next state 0, present state 1, next state 0. Where we are getting that? Present state 1, next state 0 1 0. Next present state 1, next state 1 0 don't care, 0 don't care. This is the characteristic table, the excitation table for SR flip flop. Now while you come into the excitation table, what are the things we are going to find out? In a sense, we are going to find out the flip flop inputs here. Okay, flip flop inputs. Why we are going for this excitation table? In a sense, to understand the designing. Okay, to understand the designing of the circuit, design of the circuit understanding, we are going for the excitation table. Okay. Next one is the JK flip flop. Okay, next one JK flip flop. JK flip flop. So while you come into the JK flip flop, what is the circuit? QN bar, input, K, J, clock pulse equal to 1. Okay, clock pulse equal to 1 here. This is first, this is second, first and second. Okay, so truth table. Clock pulse, inputs and outputs, state. Input J and K, outputs QN bar, state 0 1 1 1 0 1 1 1 1 0 0 0 1 again 0 0 0 1 1 0 1 1. Characteristics table. Okay, characteristics table. Present state QN, inputs J and K, and next state QN plus 1. Okay. 0 0 0 0 0 1 1 0 0 1 1 1 0 0 1 0 1 1 1 1. So 0 0 no change. Okay, no change. Similarly 0 0 1 we are giving, it's a no change. No change. 1 we are going to k, so we will get 0, here 1. So reset conditions will be there. Next 1 0 set condition will be there. So qn bar and here qn. It's a toggle. Okay. We can check this truth table and then we can derive this characteristics table. We are giving a first one 0 0. What is the output? We will get 0 0. Okay. So this 0 will act as input, 0 will act. So we have to consider the previous one. So while you are considering 1, we will get 1 and 0 here. Okay. So no change conditions will be satisfied. Similar to that of the RS flip-flop assumption conditions. Next, I am giving 0 1 here. I am giving high value to j. This 1 will access an output here. This 0, no, this is 0. This 0 will access an. So we have to consider whether it is a normal output function 1 and inverted output is 0. So similarly we will get, I am giving high value to 1 j, we got 1 here. I am giving high value to k, j 0. So the output will be 1, the output will be 0. This 0 will access an input, this 1 will access an. 1 is the input, automatically the output will be 0. So the 0 will access input, so 1. So we are giving high value to k, we got 0 here. So 1, 1, 1. So the output is 1, the output is 0 here. Okay. So automatically what is the output we will get here? Again 0, 1. So in Q1 we are getting Q1 bar, in Q1 bar we are getting Q1. So toggle. So 0 0 no change. 0 1 I am giving to high value to k, we will get 0 here. Similarly we are giving high value to j, we will get 1 here. 1 1 toggle, the percent set is 0, so the output will be 1. 0 0 no change. And 0 1 we are giving high value to k, the k value is 0. So the 1 0 we are giving high value to j, the value is 1. 1 1 it will be toggle. So the toggle conditions will be taken place under this. We are giving the input 1 1 here. Okay. While you are giving the input 1 1, automatically the toggle conditions will be taken place here. Okay. And next characteristic equation for qn plus 1. Okay, for qn plus 1. So qn jk 0 0 0 1 1 1 1 0 0 1 0 1 3 2 4 5 7 6 0 0 we will get 0 0 1 1 1 0 1 0 1 0 0 1. So we will get conditions here. So qn plus 1 equal to qn bar into k, qn bar into k bar plus qn into qn bar into j plus qn into k bar. So final answer for the characteristics equation. In excitation table, now we are going to consider 0 0 0 1 1 0 1 1. When the present state 0, next state 0. What is this? jk. Present state 0, next state 0. So 0 don't care. 0 don't care. 0 1. Present state 0, next state 1. So 1 don't care. 1 don't care. Similarly 1 0. 1 0 1 0. So don't care. 1. Okay, don't care. 1 don't care. 0 will be the output for next to 1 1 1 1 1 1. So don't care. This is the excitation table for JK flip flop, and this will be the characteristic equation for the next one. Okay, so these are all the various things. Next, D flip flop. Okay, D flip flop. It is otherwise called as a delay or data flip-flop. Okay, it is otherwise called as a delay or data flip-flop. Now we are going to draw a circuit diagram. Okay, circuit diagram. Here we are going to use NAND gate. Okay, here we are going to use NAND gate for designing. 5 NAND gates we are going to use. Okay, 5 NAND gate. QN bar. Okay, QN and QN bar. Clock pulse equal to 1. This is D input here. Okay, D input. Okay, 1, 2, 3, and this is 4, and this one is 5. So this is a circuit for the D flip flop. Okay, circuit for the D flip flop. So while coming to this D flip flop, we are going to determine. Okay, we are going to determine the truth table as well as the characteristics table. Truth table. Present state, clock pulse, okay, input, output, and state. Okay, input, output, and state. And the clock pulse is 0. So when the input is 0, automatically the output is no change. The output is no change. So when the clock pulse is 1, while we are giving the input 0, we will get no change. No change. When the clock pulse is 1, okay, when the clock pulse is 1, we are giving 1, we will get the output is 1. So the set conditions will be there. So while we are giving 0, we will get the output same. In D flip flop, what is the input that will be applied on the output? So these are all the output conditions, and this one is nothing but input conditions. This one is the input conditions. So while you come into the characteristics table, okay, while you come into the characteristics table, okay, characteristics table as well as the excitation table. Excitation table. Characteristics table, we will get present state. Okay, present state QN, input D, and next state. Okay, next state QN plus 1. Excitation table, similarly we will get present state, next state, and flip-flop inputs, and flip-flop inputs D. Okay, flip-flop inputs D. Okay, you see here, first we can verify this. While we are giving the input 0, what will happen? Here the clock pulse is 1. So 0, we will get the output is 1 here. Here also 0, 1, 1, the output will be 0 here. Okay. So this 1 will act as an input here, the 0 will act as an input here. While we are using the NAND gate, when any one input, okay, when any one input is 0, automatically what is the output? We will get 1 here. When input 0, This one will access an input here, we will get output 0. So what is the input we have given? 0, we got the output 0. This is no change. 0 is the input. Okay. While you are giving the 1 is the input, here the input is 0. So the output is, we will get 1, 1, the output is 0. Here 1, 0, we will get the output is 1 here. This 1 will access an input here, the 0 will access an input here. So 0, we will get the output 1, this 1 will access input, the output is 0. So we are given the input 1, we got the output 1 here. So table, present state 0, 0, 0, 1, 1, 0, 1, 1. 0, we will get 0, 1, we will get 1, 0, 1. So 0, 0, 0, 1, 1, 0, 1, 1. So 0, 0, 0, 0 is 0, 0, 1 is 1, 1, 0 is 0, 1, 1 is 1. So characteristic equation for q n plus 1. Okay, for q n plus 1, the characteristic equation, we are going to use two variable k map 0, 1, 0, 1, 0, 1, 2 and 3. 0, 1, 2 and 3. 0, 0, what is the output we will get? Okay, 0, 0, the output is what? And 0, 1, what is the output? Like that we are going to use here. 0, 0, so that is 0, 1, 0, 1, 0, 1, 0, 1. So q n plus 1 equal to, we will get d here, q n plus 1 equal to d. Okay. So this is the final equation for the final conditions, q n plus 1 equal to d. So this is a characteristic equation, excitation table as well as the characteristics table for the d flip-flop. Okay. Next we are going to use t flip-flop. Okay. Next we are going to use t flip-flop. It is otherwise called as an toggle flip-flop. It is otherwise called as an toggle flip-flop. Toggle flip-flop. So while we come into this toggle flip-flop, how we are going to design the circuit? Okay, how we are going to design the circuit? Qn and Qn bar. Okay, Qn and Qn bar. So clock pulse equal to 1. So T input here. Input will Qn bar. So this is the outputs, and this one is nothing but inputs. Okay, these are in outputs and inputs here. Okay. So truth table. Okay, truth table. Clock pulse. Inputs, outputs and state. Okay, inputs, outputs and state. T, Qn, Qn bar. So when the clock pulse is 0, okay, when the clock pulse is 0, so automatically the clock pulse is 0, we are going to get the no change conditions is the output, no change. 1, when the clock pulse is 1, okay, when the input is 0, automatically here also we will get no change. No change is the conditions we will get here. when the clock pulse is 1, while you are giving the input 1, so we will get Qn bar and Qn is a toggle. So only 2 inputs we are going to apply for the circuit. And next characteristics table. Characteristics table. Okay, characteristics table. Present state, input, that's a flip-flop input, and next state Q n plus 1, present state input T. So 0 0 0 1 1 0 1 1. So 0 0, so automatically no change, it is 0 1, we will get toggle. So get what is nothing but toggle. So characteristics equation, what is the characteristic equation we will get for Q n plus 1? Okay, for Q n plus 1, Q1 of T 0 1 0 1 0 1 2 1 3 0 0, the output is 0 0 1, the output is 1 1 0, the output is 1 1 0 1 1, the output is 0. So we will get isolated grouping Qn plus 1 equal to Qn bar into T plus Qn into T bar. So automatically we get Qn exclusive or T. So excitation table, present state, okay, present state as plus next state and inputs. Okay, present state is T. The present state Q1, next state Q n plus 1. So 0 0 0 1 1 0 1 1. So this is the final thing. So 0 0, we will get 0 0, just 0 0 1, we will get 1 1 0, we will get 1 0. Okay, we can verify this. I am giving the input 0 here, the clock pulse always 1 here. This input is 1, this input is always 0. So what is the output will get? This is 0 and this is also 0 0 0. Okay, we have to consider the previous output. So automatically when you consider this, we will get no change conditions. Next I am giving the input 1 here. Input is 1, we will get the output 1. Here the output is 0. Here 1, the output is 0. When 1 is the input, automatically the output will be 0 for the NOR gate. So here 1, this 0 will access and feedback, so we will get 1. So in while you are giving the input 1, in Q1 we got 0, Qn bar we get 1. So Q1 we are getting inverted output, Qn bar we are getting normal output. So Q1, Qn bar we are getting Q1. So these are all the, so that is condition is nothing but toggle. So normally this flip-flops, okay, normally this flip-flops are used for an applications, okay, where this flip-flops can be applied. In application wise, we can apply this flip-flop to one is nothing but frequency dividers. Okay, one is nothing but frequency dividers. Second one is nothing but counters. Okay, second one is nothing but counters. Third one is nothing but shift registers. Okay, third one is the shift registers. So these are all the familiar applications of the flip-flop. It is used for frequency dividers as well as counting the number of datas and shifting the datas. It can be used. So based upon this, we are going to solve the counters. Okay, based upon this, we are going to solve the counters problems. Okay, counters problems. So while you are coming to the counters problems, first we are going to define the what is meant by counters. So counter is a sequential logic circuit. Okay, sequential logic circuit consisting of 2 or more flip-flops, consisting of 2 or more flip-flops, okay, consisting of 2 or more flip-flops, and enabling, okay, consisting of 2 or more flip-flops, and enabling and counting the number of pulses, counting the number of pulses, counting the number of pulses that is crossing over the gate. So based upon the number of pulses, the output will be predicted. The output is predicted. The output is predicted. So the counters is a sequential logic circuit consisting of 2 or more flip-flops and counting the number of pulses that is crossing over the gate. So the number of pulses crossing over the gate will be determines or gives the output. Okay, gives the output depending upon the inputs. So while coming to this, what are the things we are going to depend upon in the counters instance? Suppose you take one example, it's a 3-bit counter. You take one example, this is a 3-bit counter. Okay, 3-bit counter. So we know that 3-bit is nothing but 0, 0, 0. Suppose we have to count, in counter there is an up or down counter is there, or simply the up counter is there. Okay, simply the up counter is there. While coming to this, normally we are going to determine the up counters. Suppose specifically they have asked the up and down counter, we can go for the up and down counter. So here we are going to depend upon only the up counter. So 3 bits, so 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. 3-bit instance, we will know there is a possible combination of 8 possible combinations. 1, 0, 0, 1, 0, 1, 1, 1, 0, and final one is something but 1, 1, 1. Final one is something but 1, 1, 1. So these are all the things we are going to consider. Okay, these are all the things we are going to consider for the determining of the all the things. Okay. So 0, 0, 0, 0, 0, 1. So how many number of flip-flops we are going to use? For an each bit we are going to use a single bit flip-flop. So 3 flip-flops are required for designing this circuit. 3 flip-flops are required. Okay, 3 flip-flops are required. So how would when we calculated or counted 0, 1, 2, 4, 5, 6 and 7. So 0 is the present state, 1 will be the next state. 1 is the present state, 2 will be the next state. 2 is the present state, 3 will be the next state. 3 is the present state, 4 is the next state. 4 is the present state, 5 will be the next state. 5 is the present state, 6 is the next state. 6 is the present state, 7 is the next state. 7 is the present state, 0 will be the next state. Okay, 0 is the next state. So these are all the conditions we are going to determine under this a 3-bit flip-flop. Similarly for 4-bit flip-flops, how we are going to calculate 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 and 15. So 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7, 7 to 8, 8 to 9, 9 to 10, 10 to 11, 11 to 12, 12 to 13, 13 to 14, 14 to 15, 15 to 0. Okay, so under that we are going to follow this sequence. Okay, 0 to 15 sequence we are going to follow here. Here 0 to 7 sequence we are going to follow in the 3-bit counters here. Okay, so while you are coming to this counters, we know the present state as well as the next state. So what is the table we are going to use? Excitation table for all the flip-flops. So they are given, suppose they are going to design a 3-bit counter using JK flip-flop instance. We are going to use JK flip-flop excitation table of relevant flip-flop. What is the flip-flop they have asked in the problem? We are going to use the relevant flip-flop. Okay, so these are all the things we are going to consider while you while you come into this counters. You see here randomly they are also given the counters 0, 1, 3, 5, 7, like that we will go. So 0 is the present state, 1 will be the next state, 1 is the present state, 3 is the next state, 3 is the present state, 5 is the next state, 5 is the present state, 7 will be the next state. So similarly we are going to consider like this: 0, 1, 3, 5 and 7. So 0, 0, 0. So next state will be 0, 0, 1. Next 0, 0, 1. Next state will be 0, 1, 1. Next 0, 1, 1. The next state will be 1, 0, 1. 1, 0, 1. The next state will be 1, 1, 1. 1, 1, 1. The next state will be 0, 0, 0. While we are determining the K map, okay, while we are determining the K map, we are going to solve in QA, QB, QC, 0, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 3, 2, 4, 5, 7 and 6. Okay. 0, 0, 0. So 0, the next state is 1. Okay, 1, the next state is 3. They are given the outputs. Okay, for all the other conditions they are not given the 2. So 2 will be don't care, 4 will be don't care, 6 will be don't care conditions. So all the others, the outputs will be determined. Okay, like that we are going to solve the K map here. Okay, we are going to solve the K map as well as the for designing the circuits, where we are going to follow the certain rules here. Certain rules. So under this counting the bits, okay, counting the number of bits, the excitation table have to be thoroughly known. So the present state, you take an example, the present state, next state, as well as the flip-flop inputs. The present state, next state, as well as the flip-flop inputs. Okay, flip-flop inputs will be there. So suppose we are taking JK is the flip-flop input with the QN plus 1 and QN. So 0, 0, 0, 1, 1, 0 and 1, 1. So 0, 0, 0, 1, 1, 0 and 1, 1. 0, don't care, 1, don't care 1 and don't care 0. We have to thoroughly know this excitation table while we are solving the problem for the counters. While you determine the present and next state, the flip-flop inputs are determined by using this excitation table. We have to thoroughly denote that all these things. And while you're coming to the next one, okay, while you're coming to the next one, which one in sense the shift registers, okay, shift registers, okay, shift registers, we have to calculate, okay, the shift registers, we have to calculate how many number of bits, okay, shifting the bits, okay, shifting the bits we have to know. Either it can be a left side or right side, either it can be in left side or right side. Okay, we have to denote this. And how many number of flip-flops we have to know, we have to denote, we have to calculate here, shifting the number of bits, either it can be left side or right side. Okay, we have to denote all these things. That are all the circuits we have to follow in the K map on. Okay, that all the things we have to K map on.